Thanks for being here. It's my great honor to have our distinguished speaker, Professor Surendra Shah, visiting us in Pullman. And I know there are folks online. Sorry for being late a little bit. And first of all, a little bit about Professor Shah, who's really a big name in my field. He's currently a presidential distinguished professor and director of the Center of Advanced Construction Materials at the University of Texas, Arlington, as well as a Walter P. Murphy Emeritus Professor of Civil Engineering, Northwestern University. He has been actively involved in research of concrete materials using nanotechnology to enhance performance at a macro scale. He's a member of U.S. Academy of Engineering, U.S. Academy of Inventors, Chinese Academy of Engineering, Indian Academy of Engineering, Russian Academy of Engineering, and Athens Academy of Engineering. He's also an honorary professor, Hong Kong Polytech University, Tongji University, distinguished professor at IIT and University of Jinan, a member of the Institute of Advanced Studies at HKUST, and honorary member of ACI, RINAM, and ASCE. He's also founding director of NSF-funded Center of Advanced Cement-Based Materials at Northwestern University, which included University of Illinois, Michigan, and Purdue, and NIST. Professor Shah has published more than 500 journal articles and many books. I know he has students across the world. With that, let's welcome Professor Shah. Thank you.
Okay. Good morning, everybody. Thank you, Qianming, for inviting me to visit the campus and give a talk. I know Qianming for a long time. When he was at Montana, we wrote a ERC proposal on nanotechnology. It wasn't successful, but we are continuing to work in that field. So my talk, in the beginning, I'm going to talk about more or less why we need to go in the direction of nanotechnology. As many of you know, we have made tremendous progress in the last few years in improving the strength of concrete. And this can be seen if you look at the heights of the tall buildings where concrete is the structural material. And here I've shown Burj Khalifa, which is 800 meters, more than 800 meters long, and a new building called Kingdom Tower in Saudi Arabia, which is going to be kilometer long and made out of concrete as a structural material. And this is because we know how to increase the strength of the concrete. My interest in so-called hyacinth concrete started when the construction of this water tower, iconic building in Chicago. And this was designed by Skidmore, Rowing and Merrill. And when the material supplier said that we can give you high strength concrete, and that time high strength was about 50, 60 megapascal or 9,000 PSI. They said, okay, show us how strong can you make it? So they went to the laboratory and tested a concrete cylinder of high strength concrete. And you can see this goes up to about 100 megapascal, but the failure was very brittle. So they said, how can we use such a, although strong, but very brittle, how can we use it? So that's where they came to my laboratory. At that time, I was at the University of Illinois in Chicago. And if you look at the last slide, the collapse was expansion of circumferential. So we said that it's how you test it. So if you test the material in controlling circumferential expansion, then you get a very stable response. And as I've shown in the next slide. So here I've shown stress strain curve when you compress normal strength concrete, which is about 50 megapascal here. And now we call ultra high strength concrete, which is 200 megapascal. And you can see that it's possible to get stable response. But after the post peak, you can see high strength, ultra high strength is almost like glass, vertical. So it's very, very brittle. It doesn't have what we call strain softening response of normal concrete. So in order to use ultra high strength, we have to reduce the brittleness or increase the toughness. And currently, the main way we do it is by introducing fibers. The idea behind fiber reinforced concrete came from at least initially came from the classical concept of brittle material. This is when you look at the brittle material using Griffith fracture criteria. If you look at the relation between fracture and the flaw size, smaller the flaw size, higher the tensile strength. So the argument was, the thinking was then that if you use fibers as opposed to pre-stressing bars or reinforcing, you can keep them closer. And initially the fibers we were using and still using in fiber reinforced concrete are about 30 to 40 millimeter long, aspect ratio about 50 to 100. And it turns out that at that scale, before fibers can see crack, there are lots of micro cracks. So fibers will not affect effective until the macro crack or the peak stress is response. So if you look at this response of what we use currently called fiber reinforced concrete, we are talking about 1% by volume. Fibers could be steel, glass, or synthetic. There is no change in modulus, really not any improvement in tensile strength, but substantial improvement in post-peak. So we call this fracture toughness. And this is, of course, very important in crack control. But then we said, why don't we use fibers at the micro scale? And so here I'm showing you in tension the response of fibers which are at a micron scale. This, for example, were 14 micron diameter PVA fibers, about 2% of volume. And you can see that we have now increased the tensile strength because fibers can interact with microcracks and have strain hardening response. So this was the work done in 1990s, and you can see that the material is almost like rubber, very, very flexible. And so now people are calling this strain hardening cement composites or UHPC. And as you know, that quite a bit of work done now in applying this concept. For example, here I'm showing some slide that I took from Lafarge. And what they did, they tested 4 concrete beams with this one on the left is what they call ductile, which is the ultra high performance with fibers. Next to it is a steel cross section. Next to it is a pre-stress, and the last one to your right is reinforced. They all have the same moment carrying capacity, same so-called curvature ductility, but big difference in weight per meter. So you can see that the so-called UHPC has the same weight as a steel cross section. So it's quite light, and this is one of the reasons why people have been using UHPC. For example, here are some buildings where the facade, this is in Paris, designed in UHPC. So at this point, what I want you to draw attention that when you go from macro fiber to microfiber, you can get strain hardening cement-based composite. So then the next thought is, why not use nanofibers? Because cracks start at the nano scale. And many people have been working on using several nanofiber. And I suppose the most common one is carbon nanotube or carbon nanofibers. They have amazing properties. They have a modulus as much as tera megapascal excellent conductivity. And what we are using are multi-wall carbon nanotube or carbon nanofibers. And those of you who are working with graphene-based composite, you know, dispersion is a big issue because these fibers have a very large surface area. As you can see, they are about 10 to 20 nanometer in diameter and about a micron or so long. So dispersion is a big issue, and we spend a lot of time solving the dispersion. So now we are using ultrasonication and surfactant, and we can disperse them well. And I'm going to show you some slides of performance of cement-based composite reinforced with carbon nanofiber or carbon nanotube when they're well dispersed. And when they're well dispersed, we use very, very small amount. For example, here are the result of 0.1%. And you can see these are the classic fracture tests, load versus crack mouth opening displacement. And you can see the blue curve is unreinforced and the top is with carbon nanofibers. And we have essentially doubled the flexural strength and also maintain excellent the strain softening response. Our original idea was to use this for mechanical performance, but we found out that because of the nanoscale, they also alter matrix in a ways that we did not realize it. For example, we found that addition of very small amount, for example, here 0.048%, substantially reduced autogenous shrinkage. For those of you who are familiar, when even if there is no water transport outside, if you use low water to cement ratio, there is internal shrinkage, which is called autogenous shrinkage, and that could lead to shrinkage cracking. So we want to reduce this. So here are the results of cement paste with water to cement ratio 0.3. And you can see that addition of fiber substantially reduced about half autogenous shrinkage. And we have shown that also it reduces shrinkage cracking, and also, so it can be used, it does both, reduces autogenous shrinkage, and because of the fiber form, also restrain cracking. Other people, as well as our work, we found that this material, when cement is reinforced with CNT, it could be used as a sensor. And they have excellent piezo resistive property. Here, for example, you can see the cyclic stress strain curve and measured resistance. And so we can see that you can use them as a sensor because they're linearly reversible, and you can measure remotely what is the resistance, and then you can also see what are the internal stresses. And for example, you can use them as a sensor, for example, in a highway. So if they're embedded as a sensor, you can obviously measure the speeds of the car, but people have also used them in a cold climate to melt the snow because of their good thermal conductivity. So I will come back to carbon nanotube a little bit later on, but now I want to talk about work done with other nanomaterials. For example, nanosilica, nano limestone, nano clay, and nano titanium dioxide, among others. Obviously, I'm not going to talk about it, but I want to talk about nanosilica because that's probably most commonly used in development and research material. There are many ways to fabricate nanosilica. We are using sol gel process and using it in the colloidal form so that dispersion is not an issue. So I want to show you some 3 properties which addition of nanosilica can enhance. One of them is when you use large quantity of pozzolanic material such as fly ash, which is obviously desirable as far as sustainability, but when you use large quantity of fly ash, the reaction slows down. And this is very important when you in a construction where you want a fast response. So this is one of the drawbacks when you use large quantity of fly ash. So here, for example, cement is replaced with 40% fly ash, and we are measuring the reaction with the Vicat needle test, and you can see the initial set and final set. And you can see that when we use 5% of nanosilica, the initial set and final set time is substantially reduced. And this is also mimicked in a compressive strength at early age. And this is quite important in a because you can speed up the construction using nanosilica. Not only compression, but the long-term transport properties are also improved substantially by nanosilica. Here, for example, some work we have done jointly with the institute in Spain, where we are measuring calcium leaching. This is very important in storage of waste materials, and calcium leaching means reduction in strength. So what I've shown here is the compressive strength, 7 days, 28 days, and then of normal curing, and then 63 days of accelerated calcium leaching. So the first one is uncontrolled specimen, and you can see that substantial reduction of compressive strength when calcium is leached out. So when you add silica fume or microsilica, which is very commonly used, the reduction in strength is less. But same amount of nanosilica, the reduction strength is even better with nanosilica as opposed to microsilica. The second interesting use of nanosilica, and I know I just saw briefly the work you've done here with waste material, and one of the waste material are the recycled concrete aggregate. So when you destroy or crush normal concrete, or during the damage such as tsunami and earthquake, you have a lot of rubble slab. And when you crush it, you get concrete aggregate. And we would like to use that as a natural aggregate, especially at the level of sand. But one of the challenges is that if you look at this picture, you have a natural aggregate which is surrounded by, in a recycled aggregate, a thin layer of cement mortar. This is very porous, and that absorbs a lot of water. And this means that workability is a big issue when you use recycled aggregate. So how can we improve it? And people are doing some interesting work. One way is to you carbonate this layer so that calcium hydroxide and CO2 and the pores are filled with calcium carbonate. Another way is to remove this layer by either microwave or heat treatment. So we thought if we submerge the recycled aggregate in a nanoparticle such as nanosilica, then we can reduce the absorption and almost make it like natural aggregate. So here I've shown the absorption of natural aggregate in black, recycled aggregate, which you can see is 5 times as much, and then treated with nanosilica, and you can see the absorption is reduced. So this is one avenue to make recycled aggregate more usable for making structural concrete. And then another last example I want to give of using nanosilica is in surface treatment. We know that most of the damage, durability, corrosion of rebar starts at the surface. So if we can make surface impermeable so that water and other iron cannot go, that would be very good. So currently, there are 3 ways you can do it. You can use silane, which is hydrophobic, or you can use epoxy coating, as shown in C, or you can infiltrate it with mineral particle, most common being water glass or sodium silicate. So we said, okay, why not try to see whether nanosilica can penetrate the pores and react with as a pozzolanic material. So we started with Theos, which is a precursor of nanosilica. And after Theos, after hydrolysis with water, it deposits nanosilica. And the last item shown here is alcohol, which evaporates. So I want to show you some results when the surface was treated with Theos. And Theos penetrates just like water in the pores and a controlled specimen. And you can see that we have reduced the water absorption. I want to talk about what does nanosilica do, which is different than, let's say, silica fume or microsilica. So one is the pozzolanic reaction. Here it's measured with the consuming capacity of calcium hydroxide. So you can see that when you have 4 nanometer colloidal nanosilica, the reaction is much faster. It's a couple of order of magnitude if you look at the slope than conventional microsilica. So that's one reason, the advantage of using nanosilica. Another one, we found out that the calcium silicate hydrate that is produced after the reaction has a higher chain length than microsilica or normal CSA. And this is shown here from FTIR results, and there are Q3 in when you have nanosilica. And I know that Professor she has done similar work with GEO, where using NMR, so that the nature of CSH and calcium hydroxide crystal is different when you have this graphene-based material. So this is very different than a conventional approach. We also found, using the scanning electron SEM with the energy dispersive analysis, that calcium to silica ratio is lower when we have nanosilica in the matrix as opposed to silica fume. And this means if you do some molecular dynamic modeling, you can show that lower the calcium silica ratio, higher is the stiffness of CSH. And we showed that, we proved that by measuring nano indentation using the histone nano indenter. And the advantage of this is you can see where you are indenting. And so you can find out what is happening at different nano phases. And so here I've shown the results of during from the nano indentation, you can calculate the modulus using contact mechanics, and plotted is the elastic modulus in gigapascal versus frequency of that observation or probability. And you can see from this frequency curve that when you have nanosilica, the curve has moved toward right. That means more higher stiffness of CSA as shown from the SEM analysis. So that's the difference. So now I want to talk about another interesting nano material, and that's nano clay. Nano clay is here, for example, we are using attapulgite, which is a magnesium aluminosilicate, and we do it by calcining it and by purifying, and then with ultrasonication so that it's separated into nano plates. And I want to show one very interesting observation of nanoscale in rheology. And this is becoming important, for example, in 3D printing. So what I want to show you is one application of nanosilica, nano clay in self-compacting concrete. As you know, self-compacting concrete is a concrete which flows like water, as shown here. And when the advantage is that you can pump concrete almost to a kilometer. And this is why, one of the reasons why the super tall buildings are cost effective rather than steel, because you can pump all the way to the top rather than bringing the sections one by one. But one issue with this self-compacting concrete, that when you pump concrete like water, and then when, let's say, when the concrete reaches at the top, and when it's still water, then the hydrostatic pressure at the bottom could be like water. And that means that formwork design has to be changed, because in conventional vibrated concrete, you'd be slow enough so that the pressure at the bottom is less than hydrostatic. And that's, so can we have concrete which flows like water, but still has hydrostatic formwork pressure less? And I will show you that you can do it by addition of nano clay. So what we did, so what happens that when you stop vibrating or pumping concrete, the particles coagulate and they can transfer stresses, which we call thixotropy. So like the blood is thixotropic. If you bleed it, blood coagulates and it doesn't continue to flow. So what we did is we made the cast sample of concrete with and without nanoclay and measure this, both the vertical pressure and the lateral pressure, which would be the formwork pressure. And I want to show you some results of the effect of nanoclay. Oops, I missed the slide. So what is plotted here is pressure versus time after casting. And you can see we are talking about first couple of hours, so long before what we call initial set. And the pressure is increased step by step. So this is the vertical pressure, and this is the measured horizontal pressure of the control specimen. If it's water, then the vertical and horizontal would be the same. But because of thixotropy, the horizontal pressure is less. But when you add the 0.3% of nanoclay, the lateral pressure is reduced even further. And this is very important. And as those of you who are working now with 3D printing, you can see that when you have a layer by layer construction, you want the bottom layer to support the subsequent layer. And the thixotropy can be a very useful tool. Now, we have a lot of people are working, and we are to understanding what happens during mixing, that's understanding the rheology. So one of my former PhD students now is in Korea, and he's developed this rheometer, which is a parallel plate. I don't know whether I can use this. No, parallel plate rheometer with a window where the laser is signed, as you can see in the side. And from the backscatter laser light, you can calculate the size of the particle. And as you vibrate it, how the particles coalesce when you have nanoclay or superplasticizer. And so this is a very important study. And I'm not going to talk about detail, but it's quite, I thought I mentioned. Now, in the last part of my talk, I want to talk about what we call metamaterial, and in particular, metaconcrete. Well, what are metamaterials? So in traditional material science approach, you process material, examine the microstructure, and connect it with property. For example, let's say in concrete, you make a mixture, add whatever you want to add, and then see what happens in microstructure and measure property, compressive strength or whatever. In metamaterial approach, you say what property I want to improve, whether it's compressive strength, fracture toughness, transport property, and then how I can fabricate at the nanoscale hierarchical architecture. And the key is how I can fabricate that. So I want to give you two examples of this approach. One came almost accidentally to us. See, what happened that there was a roundtable meeting of all the people in Chicago area, ready-mix concrete and admixture and the structural engineer. And they want to increase the modulus, double the modulus of concrete. You can say, why do I want to double the modulus of concrete? So this is because with the super tall building, strength is of course important, as I mentioned earlier, but the deflection, either due to wind or earthquake, becomes very important. So they want, for this good design of super tall or tall building, modulus close to 60 gigapascal or 8 million PSI. Now, currently we have 4 about. So how do we double it? Well, the only way that is being done now is increasing the strength. So this is a classical plot of modulus of elasticity versus compressive strength. This is, for example, a Hong Kong code, similar to ACI code. And if you look at it, if you want 45 gigapascal modulus, then you need compressive strength of 140 megapascal. But the designer are perfectly happy with 100 megapascal as far as strength. But they're using this higher strength for higher modulus. But higher strength means higher cement content, higher cost, and as we know, the material is also more brittle. So is there another way? So after that workshop, I went to our group in our lab and see, we have not really paid much attention to modulus with addition of nanofiber, carbon nanotube. So here I have shown modulus of cement paste and with 0.1% of multiple carbon nanotube. And you can see we increase the modulus about 60%. But this is carbon nanotube or geo, but they're added at the nanoscale on the cement. But of course, high-rise buildings are not made of cement, but made out of concrete. And we are not doing anything to aggregate. So we suspected that when we have the same amount of nanotube in adding sand, the effect will be proportionately less. Well, we were surprised that was not the case. So this is the mortar specimen, same amount of nanotube, 0.1%. But you can see that we have increased the modulus even more, even though we are not doing anything to the sand. Then we check concrete, and to our surprise, if you do a normal composite material approach, the increase will be very little, but here we are adding 0.1% by weight, but here you can see we have increased. So then we decided, okay, we tested many concrete specimens, and here are one set of results. So if you look at plain concrete and concrete in the bottom with 0.1%, there is not much increase in compressive strength, but substantial increase in modulus of elasticity compared to plain concrete. So what does that mean? That means if you look at the chart I showed you before, here we are, but when we add 0.1%, I get 45 gigapascal without increasing compressive strength. That's substantial reduction in cement and sustainability. So this is one of the important attribute of carbon nanotube. Now, why does CNT or carbon nanofiber proportionately more effective in concrete than cement paste? Well, clearly you can probably see the idea is the interface. The interface between aggregate and cement is rather porous, and we suspected that addition of nanofiber alters that interface. To check that out, we did some combined analytical and experimental work. So first we look at the solution of three-phase material, spherical aggregate surrounded by annulus of interface in a matrix, infinite media, and you have a analytic solution if you know the modulus of three phases, aggregate, interface, and the matrix. Then we made two sets of concrete specimens, one with less aggregate and one with more aggregate. But to use that model is only good if the aggregates are spherical. So we calculated for each aggregate by doing a grayscale, each aggregate, what is their surface area equivalent sphere. So we can then calculate using analytic the modulus of the composite and then do the FEM to calculate the modulus. But each of the aggregate has a number and a different modulus. So then we did FEM analysis, and before I go to the model, we need to know three things. We need to know what is the modulus of aggregate. And to measure the modulus of aggregate, we pick some aggregate randomly and using ultrasonic pulse velocity measured there. To modulus of matrix, obviously, is a conventional ASTM test. Modulus of interface was somewhat challenging because interfaces are in few micron wide. And if you use classical nano indentation, because they leave the indent which are few micron, so you really cannot measure the interface. So we use AFM in a quantitative nanomechanical test, and I've shown some detail here. So you can see that we have for a 10 micron by 10 micron, 250 by 250 measurement. So the scale is in the nanoscale. And when we're using AFM, as I've shown here in the, from the slope of this curve. And so here I've shown the modulus as measured with this AFM of matrix with interface with and without CNF. And clearly you can see that with CNF, which is blue, the modulus is substantially higher. And so then we put this measured value in the analysis. And so all the three measured value and the predicted value, and you can see that the match is very good. The important thing to note is sample 1 and 2. Sample 2 had twice as many aggregates as sample 1, but increase in modulus is not that much because of the weak interface. But sample 3, which had CNF, the modulus is substantially increased. Then we also did, and we are continuing to doing that, is see what are, for example, calcium to silica ratio in the interface when there is a carbon nanofiber and without. And you can see calcium to silica ratio is different. We have also shown that the size of calcium hydroxide crystal are smaller with CNT. So the addition of CNT fundamentally alters the material at the nanoscale. And this then increases the modulus. The second example I want to give is in the surface coating. I remember I mentioned that when you have surface treated with TEOS, then it deposits this nanosilica, and with the pozzolanic reaction, you have pores filled with CSH, and that it improves the permeability. But if you compare the absorption of controlled specimen with TEOS or sodium silicate or water glass with silane, which is hydrophobic, silane is much more effective in repelling and not having water transfer. But there are other disadvantages of silane. So can we combine the hydrophobicity of silane and the pore filling of a nanosilica? And this is the work that we are doing with the Jinan University. I think Qianmin is also involved with Jinan University. And this is, we are using so-called core shell approach. So you synthesize a core of nanosilica, I mean, it's a core of silane surrounded by nanosilica. And the process, the fabrication process is shown here. And we have shown using XPS and other things that there is a strong bond between the silane and the nanosilica. So now when you look at the results of absorption test, treated surface, untreated, control, TEOS, silane, and silane at silica, that's a core shell. So we have combined both and substantially improved the impermeability. So I think this is now the direction, interesting direction to go as far as application of nanotechnology is concerned. So I want to summarize and then talk about briefly what direction we are going. So we meant nanosilica, as I mentioned, is a widely used nano particles and many advantages in high volume fly and calcium leaching, in improving absorption of recycled concrete aggregate, in surface treatment, as well as in the modification of nanostructure. Nanoclay, I only talked about rheology, and as I said, it increases thixotropy, but people have also shown that addition of this calcine purified nanoclay has a lot of improvement in durability and other property as well. Carbon nanotube, we talked about it, and briefly we talked about metamaterials. So currently, what directions people at my group and other people are taking? Well, the cost is, of course, a major issue when you talk about construction material. And I like to point out that we are talking about using carbon nanofiber or carbon tube as an admixture. So we are talking about 0.1% by weight of cement. So it's very similar to cost of admixture. So could be cost effective. But the main issue is still the dispersion. We have done it in the laboratory, but scaling up is obviously a key issue. And we have now started in that we have ultrasonicator at somewhat large scale, so we can do it the large scale so that we can test large scale concrete specimen. The core shell approach has many possibilities. One of them is this titanium dioxide. Now titanium dioxide has been used to have so-called self-cleaning surface because of its property of titanium dioxide. It oxidizes the pollutants and washes out photocatalytic activity. So like currently, for example, this is an extension of Kennedy Center in New York, where they use titanium dioxide mixed in concrete. But titanium dioxide is expensive and you don't need it in the whole concrete, you only need its surface. So why not do it at the surface? Well, the issue is that when you put titanium dioxide spray on the surface, it doesn't bond well, and the bond is very weak. So work has been done to have this titanium dioxide at silica. So you have a core of titanium dioxide surrounded with nanosilica. So you have both hydrophobicity and core filling, and they have shown very good results with this. So then it's also cost effective because you only do it in the surface. There is a lot of work. I only talk about carbon nanotube, but there are obviously other nanofibers, quite a bit of work being done at nanocellulose fibers. We are continuing. And I only talked about CNT, but quite a bit of work done with, we call sort of graphene-based composite. For example, Professor Shih has done quite a work with GO, graphene oxide. People are working also on reduced GO and with the graphene type of material. So and in fact, RILEM has just started a new committee on graphene-based composite, where both Professor Shih and I are members. When you use this graphene-based composite, such as CNT, they are conductive. I showed you with their piezo resistivity. So if people ask, what about the corrosion of rebar? Because corrosion of reinforcing bar involves galvanic current. So that's an issue. We have found out that in fact, when we add CNT, corrosion is delayed. And we are still exploring it, but one of the reasons is at the frequency. At the galvanic corrosion happens at almost DC level, where fibers are not there, not more insulating than conductive. So that is one area. We are now increasing the ductility by applying, let's say, nanofibers or microfiber. But can we have at the molecular level? There was earlier work done, some of you know, called macro defect-free cement, which has an inorganic and organic bond. And some work is done in the CSH layer to have introduce organic modular, organic to improve element to improve the ductility. And clearly with the nanomaterial, people always, we have to worry about the health. And so far, at least with CNT, people have shown that that's not the same health problem issue that you have, for example, with asbestos fiber. So I hope I gave you some idea about what is happening as far as application of nanotechnology to cement-based material. So thank you.
I'll ask one. Thanks for the inspiring presentation. Professor Shah. So on the nano clay, hard to demonstrate, improve rheological behavior. You mentioned a type of nanoclay I'm less familiar with. I'm more familiar with the Montemorne.
Yeah.
Can you comment on the difference?
I don't really know. People have used nano kaolinite quite a bit, and we have used this attapulgite. I don't know whether any work being done with Montmorillonite clay, but if you can calcine it and separate it, then it will be worth looking. Then, yeah. So that we. Which, yeah, and you can get separated. Oh, very good. Yeah, that's a good. Yeah, yes, you are doing it with. Yeah, that's. Yes, please. You want a mic? Because of the online.
So interesting that you did some scale up to concrete testing, because it's just difficult with nanomaterials and the scale that they're available to actually go and test in concrete. So it was really interesting that you showed that progression from the paste, the mortar, and the concrete. Can you speak a little bit more about why you think that the improvement, I think it was in modulus, even increased as you scaled up the concrete?
Yeah, well, that's a very good point. I think, we have done a lot of work with nanomaterials, but the application in the field is still not significant. And there are several reasons. One of them is most of the work done in the laboratory, obviously, the nanoscale is done in cement, while industry is interested in concrete. So when we talk about admixture suppliers, they say, yeah, that looks very interesting. And so can we cast a big slab and show to, then it's issue of scaling up. So that's certainly one thing. Now, why the nanomaterial were more effective in concrete and cement is because in the normal concrete, you have, let's say you have a cement matrix and aggregate. Aggregates are substantially stronger than cement, but we don't get that much out of aggregate because of weak interfaces. And so if we densify the interfaces, then we can increase the compressive strength. And this is, of course, the idea behind ultra high strength concrete. Ultra high strength concrete, we have because of the silica fume, we densify the interfaces. The difference between densification with microsilica and with CNT, because as I show you that it really alters CSH. It changes, elongate the CHS chain length, reduce the size of the calcium hydroxide crystal, changes the calcium to zero. That's a big difference. So it does modify interface in a different way than with the classical silica fume. And I think this is where more work has to be done, because I have seen some work coming from Sherbrooke University in Quebec, where they showed that addition of nanocellulose also increases the modulus. Well, if you compare the modulus of nanocellulose with carbon nanotube, it is orders of magnitude different. Carbon nanotube, we are talking about terapascal or CN or nanocellulose would have. So why? And I think the answer lies really in modification of interface, and we have to. This is where we have to, emphasize. Well, yeah, that's a very good point. Initially, we all thought that, this is the main advantage of adding nanoparticles. And with certainly it's true with nanosilica that we have shown with CS, it's not clear that the results I've shown are contradictory. I don't know whether you agree with GO2. Sometimes it shows, yes, it increases the rate of hydration and others not. But what is your opinion? Yeah, it doesn't. No, I know. So you are talking about you. Yeah. So I don't know.
So the nucleation effect, actually, it's interesting we're talking about this. We have a paper right now reviewed by CCR, which is look at the CNTs. We try to demonstrate that CNTs actually don't provide nucleation sites because but the geo does. So the two are quite different.
And why is that?
I think the surface chemistry and also the microbiology, my theory, which has no proof because maybe the double layer, especially with the CNT, creates a very localized environment where the ionic species are interacting with that double layer. But again, it's hard to demonstrate directly.
But the substrate treatment are also, and that may also be, when you CNT is not commodity, how it is made and what are the surface. So that could also influence the results. But I would initially say that should not be the main reason to use GO or CNT, increased rate of hydration, but other properties which are dramatically changed. And that's what. Yeah.
Sometimes you have a parking effect. Sometimes you have an acceleration effect.
Yeah.
We saw this just a few days ago. We submitted another CCC where unzipped CNTs, which is like a very interesting quality and with a lot of surface oxidation.
Yeah, I don't know whether we should transfer the mic. I hope if people others can hear too. Answer. Okay. And I think that a lot of work has been done. Let me say, UHPC, as I mentioned, cannot be used as a structural material without fibers. So currently most common is 2% more or less steel fibers. And that is the one common way. However, the emphasis that has more on the strength and less on strain hardening. But strain hardening is also very important. And there, the work I've done with Hong Kong Poly with the dye, we have used 2% of high density polyethylene, and we get 20 megapascal tensile strength and 8% peak tensile strain. And that has a tremendous influence in the ductility for the use of the structures. So there's a lot of work being done there on microfiber for UHPC and strain hardening cement composite. People are also using carbon fibers, mesh. A lot of work done with textile of carbon fibers and glass fibers. Thank you. Yeah, let's look at that. Because I was reluctant to go out during question and answers, but I couldn't hear her well. So I hope that.
Yeah, I'll probably send you some of the papers. We're talking about these two
Yeah, I
issues.
think
The
Geo